Okay, we're back with part 2, day 59, I think it is, day 59, part 2. The question is, in the compound interest formula, what would have to be known or set as constants to leave a linear equation? Well, let's have a think about this. Remember, what we want in a linear equation is to have something that looks like that, or something that looks like y equals mx plus b. And notice there's no plus, there's a plus inside the brackets, but there's an exponent on that. It's not like the b has an exponent on it or something like that. That doesn't make any sense. So what do we want is we want it to end up probably looking like this. So we want to sort of get rid of somehow all these this exponent. And if I chose this to be an exponent and then left I as the variable, well, then we're going to have kind of x to some exponent. We're going to have x to the exponent n, and if we pick n to be something like 5 or something like that, well, then we'd have a fifth degree function. That's not what we want either, is it? So how do we end up with a linear function? Well, we need this whole thing to be numbers. If this ends up being the slope, m, then we'd be good, because then this could be the x. So I'm going to say p is, let it stay as the variable, and then we're going to choose some convenient values of I and n. It says what would have to be set. So let's say I and n are constants. So for instance, if I pick I to be 1 and n to be, let's let n be, what are we going to let n be? N is going to be 3. Why not? So what would we have? We'd have A equals P. By the way, an interest rate of 1 is 100% interest, which is pretty wicked, isn't it? But oh well. A equals P times 2 to the exponent 3 is 8. So then I have an equation 8p. That's the same as the dependent variable is a, the independent variable is p. That's a linear function, isn't it? That's a linear function. And as it says, check with the TI-83, we will do that later. So a quadratic equation, we want to take this and end up with a quadratic equation. That's the general quadratic equation. Just like the linear model, we're going to chop off the end part and aim for that. Well, how do we, kind of lines up. If a is a value, then we're going to let p be a value. The x, the independent variable, is the base, right? The base of the exponent, where n, it looks like n has to be 2. We need to let n equals 2. P is going to be some initial value, doesn't matter. I'm going to let it be 1 just to make it the easiest. And then we're going to leave I as the variable. Leave, that's bad, some bad handwriting there, as the variable. Okay, so then what does it look like? P is 1, I is the variable, and n is 2. So if I think of the independent variable I and the dependent variable a, I got y equals 1 times 1 plus x squared. Does that look like a quadratic equation or quadratic function? Well, we'll check it on a TI-83, but it looks good to me. An exponent x and or exponent 2 on variable x, that makes it a quadratic. An exponential equation. I'm losing my my graph is way up there. I'm going to rewrite it here, or my original formula. So an exponential equation looks like this, remember, where the independent variable is in the exponent. So we're going to have to leave n as a variable. and choose the other things to be whatever, right? So the x has got to be the exponent for an exponential function, and then p and I will be constants. And we'll pick them again. Again, I'm just going to let p equal something easy, and in fact, I'm going to let I equal something easy here as well. So hopefully we can recognize this as a exponential function. P is 1, 1 plus 1, and then the n, I'm leaving it as a variable. 1 plus 1 is 2, 2 to the exponent n. Does that look like an exponential function? It sure does. And it says check with the TI-83. Well, let's check it on the TI-83. I've actually put these in there. I've put these in there. I put these in there. Here we go. Our first one was a equals 8x. The second one was p was 1, I was the unknown, and the exponent n was 2 for a quadratic equation. And you see the one that we just figured out. And if I press, I'm going to go zoom decimal. These go pretty fast. Linear, quadratic, exponential, just like we were asked for. Perfect. All right, example 3. Or is this example? Is this, yeah, example 3. Good. Big, nasty, long formula. All right, this formula, nasty formula. C is the contestants remaining, B is the number of contestants at the start, N is the number of contestants eliminated per round, and R is the round number. And I kind of consider this, I'm thinking of this equation as, it's almost like a World Series of Poker thing, right? Where after so many rounds, the people, we can figure out how many contestants are left over. So here in this equation, C is not known, B is 1,000,000, N is 8, which means 8 people are eliminated per round, which is kind of the size of the poker tables. So each round is, each table would have one winner, I guess, and then they move on to the next round. This is after 4 rounds. How many of the original 1,000,000 people are still left over? Well, not many. 1 over 8 to the exponent 4. And then you put that all into a calculator in one step. This is one of those formula ones, an equation that I just solved for the dependent formula. This is 244 in a decimal. There's some decimal places there. There would be 244 contestants at the end. Contestants. About. What would have to be constant to make it a linear function? So this idea, the linear function, is we don't want any weird stuff going on. We just want y equals mx. Well, all the same trick as the compound interest formula is, if all of this is known, if all of these are constants, then b can be our unknown. So for instance, if n is 2, that would be 2 people per round. Almost just half the people are eliminated per round, rather, and that would be almost just like a basketball tournament or something. Maybe the round number can be 3, and we'll see what happens here if we end up with a linear function. That was the goal, a linear function. B, I'm leaving. B is going to be our variable. And then I'm left with 1 over 2 to the exponent 3. And see, that's all number, right? 1 over 2 to the exponent 3 is 1/8. Which then that looks like a slope, doesn't it? and we'll check that with the TI-83, but does that look like a line? Absolutely. Okay, quadratic function. Now this one's kind of weird because we know the exponent on a quadratic function has to be 2, right? So that gives us the idea that r equals 2. It has to be round 2. But then the x value, the unknown has to be the base of that, right? So n we're going to leave as a variable. And as we'll see, this one actually isn't quite a quadratic function. This is as close as we're going to get, and then b can be any old thing that we choose it to be to start, like 5 people to start or whatever. Doesn't matter. I just want to make it to be a quadratic function. So I have c equals 5 times 1 over n. I'm leaving that, and then that's the exponent 2. Notice, does that kind of look like a quadratic function? Well, if I call that x, it's not quite. I realize that it's not quite because of the 1 over, right? But it kind of looks like that, kind of quadratic. The 1 over business actually makes it so it's not quite, but we're gonna pretend. We're gonna pretend that's the case. What about an exponential function? Well, an exponential function, we want the independent variable to be in the exponent. Well, that's no problem. We've got an exponent with the value of r, so r will be the variable, and then we'll pick other stuff. Again, just for fun, we could pick anything we wanted to. B equals 5 and n equals 2. Then I'd have c equals 5, n equals 2, and then the exponent r. Well, does that look like an exponential function? It certainly does. This looks like this exponential function, doesn't it? Where my dependent variable is c and my independent variable is x. This actually looks like a half-life question, doesn't it? With half as the independent variable. And in fact, a lot of basketball tournaments, tennis tournaments, all that stuff, where the losers go home, this would be the type of model, half-life, because half the people are eliminated each round. Let's check it on the TI-83 real quick to see how that worked out. The first one was the 1/8b. The next one was this 5 times 1 over n to the exponent 2. And we'll see that one doesn't quite work out, but we'll talk about that in a second. And then the exponential function this is going to be an exponential decay function because the base is less than 1. Oh, let's have a look. Oh, I'm going to graph it so I can talk about it as it goes. First one is the linear one. This one is the weird one, right? It doesn't look like a quadratic quite. There's the exponential decay function just like we expected. Okay, now this one, because of the 1 over business, in fact, that ends up being the same as n to the exponent -2. Now suddenly something weird's going on. It's not a polynomial function at all. But if I graph that one instead, certainly I could convince you that that's a parabola, right? Linear function, parabola, quadratic function, and then there's the exponential decay function. Okay, so that one was a little bit weird, but it fits. Not bad. Okay, so try your homework. That's the end of the formulas business. Stay classy, MCT4C.